Now, if you look at A21 here for this matrix, and you look at this entry here on the A transpose, you will see that this is A12. So now if you search for A21 on the A transpose, you will see that the A21 is actually the first row and the second column of A transpose. So I will write it here. A21 is first row, and second column of A transpose, while it was the second column and first row of A. So that's what this expression say. All it says is that the element Aij, the ith row and jth column of A, is the element of Ji of A transpose. That's all it says, and that's what we saw here. The first row and the second column of A transpose is equal to the second column and is equal to the first row and the second column of A. First column, second. So all it says is that the element in the first row and the second column of A transpose is the element in the second row and first column of A. That's what it says. Now, if, as I said, if A is m by n, then A transpose is n by m. Also, for now, ignore this one. I said it's zero flop, so we'll talk about the complexity later on. So now addition. Addition is defined similar to the vectors. If, first of all, in order to add two matrices, there is one condition only. They should have the same dimension, because we are going to add the corresponding entries together. So in order to add A and B, they should have the same dimension. Now, if A is m by n, B must be m by n as well. Now, when you add them up, this means that you are adding each entry, each corresponding entry. What do I mean? It means that you are adding A11, the first row and the first column of A, to the first row and the first column of B, all the way to that m row and the nth column of A to the nth row and nth column of B. That's what this one says. Okay, so how many addition do we have? As many as number of entries we have in a matrix. How many entries we have? M by n. M times n, right? So remember, this is important for when we get to the complexity. So addition, as I wrote here, is add the corresponding entries of the matrix. Now, we have properties of addition that are fairly basic. It says that A plus B is equal to B plus A plus B plus C. We can switch the order. We can write A plus B plus C. First, we can add actually B plus C and then add that to A. And now this one that is quite important, A plus B transpose, is you can bring the transpose inside the parentheses. You can say the A transpose plus B transpose. So it's like a linear operator transpose, right? So A plus B transpose is A transpose plus B transpose. As a matter of fact, let's use C1a plus C2b transpose is equal to C1a transpose plus C2b transpose. Scalar really does not change anything. Now, let's talk about multiplier matrix by a scalar. So consider we have a scalar C and matrix A. So multiply matrix A by constant C or by a scalar C. Would be better to use a scalar here. Scalar C is a result in multiplying C by each entry of A. What does it mean? It means this. If we have C and then we define A as before, as A11, A12, all the way to A1n, all the way to AM1 to AMN, then you're going to go ahead and multiply C by every single entry. So C is going to multiply the first entry, C is going to multiply the second, all the way to the last entry in the first row, and then you're going to multiply C by every single entry. How many multiplication we have? As many as number of entries. How many entries do we have? M by N, M times N. It's important for a complex. Now, the properties, now assume the C1 and C2 are two constant or two scalars. Then C1 plus C2A is equal to C1 times A plus C2 times A, right? So what it means is that if you have matrix A, A11, A12, all the way to A1n, AM1, AMN, and then you have C1 plus C2, then what you can do, you can first multiply C1 by this matrix plus C2 by this matrix. It's the same thing. Now C1a transpose is the same thing I talked about that here. Is equal to C1a transpose. So C1a transpose is equal to C1 times A transpose. Okay, C1 is unchanged and then you transpose A. Now we get to a little bit more complicated concept, which is matrix norm. Remember we had a definition of Euclidean norm or L2 norm for a vector. So Frobenius norm is the equivalent of L2 norm for matrices. So usually you can show it also like this, Frobenius norm, right? What this statement says is that Frobenius norm is a sum of a square of all the elements of a matrix. What it means is that if you have matrix 1, 2, 3, 4, then the Frobenius norm of this matrix is what? Is a square root of 1 square plus 2 square plus 3 square plus 4 square, which is equal to a square root of 30. That's the Frobenius norm. It's very similar to the Euclidean norm of a vector. Now we're going to relate them together in just a moment. Now there's a concept, as we defined in a vector, was a RMS value of a matrix. Now remember RMS value of a vector. When we had a vector x, the RMS value of a vector, that's the vector x, is this. x1, x2, all the way to xn. It has n entries. The length of a vector is n. The RMS value of a vector was defined as a norm of vector divided by a square root of n. So it was a way to normalize or standardize the vectors with different length. When you want to compare the norms of vector, so if you have more entries, the chances that you have more non-zero element, and then the norm might be actually larger value. So in a sense, with the RMS value, you can actually standardize that. You can normalize that by square root of n. The same way, you can define this one for RMS value of a matrix. So this one will become the Frobenius norm, or the norm that you want to define, whichever norm you would like to define, as long as you're consistent. And then this this one is the square root of total number of elements. Square root of total number of elements. So I want to stress out that these two are the same. The vector, this was also total number of elements in the vector, or dimension of vector, total number of elements. Okay. So now matrix norm satisfies all the norm properties. So we have some properties defined for all the norms. So matrix norm also, Frobenius norm also satisfies these properties. One is that the norm is non-negative. It is that it's always greater than or equal to 0. And the equality to 0 happens only if the matrix is 0. So if you have a 0 matrix, the norm is 0. Otherwise, norm is always positive value, always. So then this property says that when you multiply matrix A by a scalar C1, remember norm is always non-negative. When you are bringing this scalar outside the norm operator, make sure that you bring it with the absolute value, because norm is always positive. So this side is always positive, greater than or equal to 0, or non-negative, and then this one is greater than or equal to 0, so this one better to be greater than or equal to 0, and that's why we need absolute value. Triangular inequality, remember for vectors was valid when we had defined a norm of a vector. It's the same thing. It's actually valid for all the norm operation. So also when A and B are matrices, the triangular inequality holds. This one is a new one. So norm of A and norm of A transpose are the same. Why is that? So remember, A and A transpose have the same elements. The elements are the same. You're not really doing anything to the elements. You're just swapping the place of rows and columns. So A and A transpose have the same elements, right? So here I said, what's the definition of Frobenius norm? It's just sum of a square of all the elements of matrix. You have to sum them up. You can use any order you like. So here you can start from 4 square first, and then go ahead and add 2 square to that, and then go ahead 1 square, and then go ahead and add 3 square. So think of it like that. A transpose, the rows and columns are switched as opposed to A, but eventually you're going to add the square of all the elements. So you need to consider all the elements. Therefore, since A and A transpose have all the elements similar to each other, exactly the same, then the norm, the Frobenius norm is the same. It's going to be clear here. Now we go to talk about another very important property of the Frobenius norm. So remember here the definition that I have. Let's use another color here. What it says is that, for example, let's go ahead and copy this one and paste it here. Okay, let's paste it here. Good. Now, what this one says is that, first of all, you can switch the summation sign. Let me show that. J from 1 to n, I from 1 to m, aij square. Okay. So now, for example, this is a matrix A that you have, like always, A11, A12, all the way to A1n, AM1, AM2, all the way to AMN. Now, assume J is 1, and then vary the M, vary the I value. So assume that we are in the column 1. Remember, J is the second index, Aij. J indicates the index of column. When J is 1 and M is changing, means that we are talking about the first column. So let's just do that. If J is 1, what we are going to do is that we are considering A11 square plus A21 square all the way to AM1 square. So we have this one here. Plus, let's J to be equal to 2 and vary I from 1 to n. Then we are in the second column. This is J2. This is J equal to n. Then we have A12 square plus A22 square all the way to AMN square. Okay, good. So what is this one? What is this? Remember, for a definition of a norm of a vector, this one is nothing but what? The square of norm of the first column. You can define it like this: A1. Remember, we had the definition of writing a matrix as a column, block and block row. So they can define this one as the norm of A1 square. That's what this is exactly. Because norm of A1 has a square root of sum of a square of all the elements. So when we square that, we get rid of that square root. This one is what? This one is norm of A2. A2 is what? The second column. Second column of A. So in a sense, you can define the norm of A square as this identity. So what this one says is that it gives you another way to calculate the Frobenius norm of a matrix. So this is the Frobenius norm, this is the L2 norm. You sum them, you add them, norm of every single column of matrix A. So you can use the definition I had in the beginning for the Frobenius norm, or this definition, but this one gives you pretty good intuition as how you can actually calculate the Frobenius term as a sum of the norm of the columns of a matrix.